Hello, everybody. I thought I'd help you with the problems since you really don't have the textbook and many don't have access to it. So I put up the problems here and I'm going to comment on what goes on with each of them. The first question is you are sending 1,000 bytes across a line. The line is 25 kilometers long, and the propagation speed is 2.5 times 10 to the 8th meters per second, with a transmission rate of 2 megabits per second, so 1,000 bits per second. So what you have to think about is this. It's again, remember that we have distance equals time times rate. So what we've got here is we're talking about a distance of, say, 2,500 times 10 cubed meters. And we're going to rearrange this here. Is same as time equals distance divided by rate. So now you've got that number of minutes divided by 2.5 times 10 to the 8th meters per second. If you look at that, you invert the denominator and multiply. So what you've got, you're going to have meters in the denominator and seconds in the numerator. The meters will go away, and you're looking at 2,500 times 10 to the third divided by 2.5 times 10 to the 8th. Now that is the time for a bit to move down there. You'll notice I did not take into account how many bits there are. This is the time for one bit to move from A to B. Source, I guess from A to B, where those are the two endpoints. Now, that is how much time it takes one bit. We have to put the bits on the line. So it takes us 2 megabits per second. It takes us 1 second to put 2,000 bits on the line. That means we get them from our machine down to the medium that's sending it away. So we are sending 1,000 bytes. Which is 8,000 bits. So what you have to look at is the full time equals propagation time plus the time to get on the line, which, remember, is same as the word transmission rate. Now that works because you think of it this way. When you put the last bit on the line, then that bit takes this time to get across. So it takes, so you have putting it on the line and getting it across. And you can then think about the rest of that problem. Problem 2. Now this one is not that hard. Again, you're sending stuff across the line. Well, your first line can move 500,000 bits per second. The second one can do 2,000 bits per second. Pardon me, 2 million bits per second. And the third one can give 1 million bits per second. Now, if you're passing them through, the slowest one is going to be the one that determines how fast they can go. You can't get them through there faster than that. So in a second, you're going to get 500 kilobits through that line, R1. Now, it doesn't matter how fast R2 and R3 are at this point, because you're only going to get 500 bits to that point before they can start sending them. You have a bottleneck. And that's the way to think about this. Think of what the minimum is as you send them through. Throughput means how many you can get through in a certain amount of time. Now, problem 3 is a little more interesting and perhaps a little more complicated. They say it's elementary, but we'll talk about that. What you need to do in this one is we're thinking about 2 possibilities. One's called packet switching and one's called circuit switching. I mentioned those on the last video. In circuit switching, you have to dedicate a line to sending one message, and you have to keep it open if that particular computer or node is going to send its message. Now, that means that we have I hope I'm doing the right one. Oh, pardon me, I'm not doing the right one. I'm sorry. What I was saying was for the next one. Okay, it just says, as with problem 1, we're doing things now in terms of symbols. It's the same kind of problem. It's just you're switching to symbols from actual numbers until you get down to here. Remember, the propagation speed is how long it takes one bit to get down. The transmission is how much time it takes you to get the bits on the line. This one is the one I was more interested in. We have a line can send 3 megabits per second. We have a user that sends 150 kilobits per second when they are transmitting, but they only transmit 1/10 of the time. Now, if we use circuit switching, we have to set up one line for each user. So with circuit switching, each user needs a line that can send 150 K per second. We have a line. I need a virtual line, I'll say. Switch FWITCH, pardon me. We have a line that can send 3 meg per second. The question is, how many virtual lines can we create in our 3 meg line? Each one of them has to be separate, and it has to be dedicated to one machine. So the number of machine users we can have is how many virtual lines we can set up. Now, the next part's a little more complicated. Now we're going to switch to packet switching. Didn't mean that as a pun, but I guess it came out as one. We will use packet switching. Now, before I do that, I just want to mention something about the first choice in A. Some of those lines aren't going to be used very much. Each one of them is going to be out of use and idle 90% of the time. That's an awful waste of the bandwidth, awful waste of how much we could send. Packet switching is going to help us fix that. Now, with packet switching, we don't have to set up the lines ahead of time. The probability that one user is transmitting is 1/10. Now, the question is, how can we figure out that there are 21 users sending? And this is a probability problem. What we're going to do is say each user has a probability of sending of P. So P is, in our case, P equals 0.1. What that means is at any given time, the probability that that person is sending is 0.1. Well, of course, that means the probability they're not sending is 1 minus P, which often is called Q when you're doing this. So how can we tell if 2 people are sending? Well, here's the trick. the chance that only that one or two are sending at a given time, and I should say 0, 1, or 2, or 2 users are sending at a given time, we say to determine, let's do it that way, to determine the probability that at 0 or 1 or 2 users are sending at a particular time, we can calculate the probability that 98 users are not sending, because the probability of either 0, 1, or 2, I think that works. That's basically the way they do it. Maybe a little off, but my algorithm seemed to work. But the trick is, which one or which two are sending? And that requires us to play some games. Actually, this is known as the binomial distribution. And I created a Excel sheet for it. So I'm going to go and look at the Excel sheet now and try to show what I'm doing with it. So it's this one here. So N is the number of users. This is P. P is the probability that a user is sending. And I set this up for 100.1. The material is live, so if you want to change this number, you can change it, and you'll get the answer for that. Now, that's these two. I want to know the number of transmitting. So little n is the number that I transmitted at a given time. And what I want to know is what's the probability that 0 are transmitting, 1 is transmitting, 2 are transmitting, 3 are transmitting, so on. So the probability that, say, 2 are sending, we get by first looking at all the possible 2 users who could be sending. This means we need to know how many groups of 2 are there in cap N. That's what we're after. So how do we do that? Let's see. That's what's known as a combination. This is CN2. And by definition, it's the following. Well, you can prove it's this, but I'll just give it by definition at this point. It's capital N factorial divided by N minus the 2 factorial times 2 factorial. Now that looks like a horrendous number. Well, it is, but it's reason you can manage it by a lot of crossing out of a lot of things. That's basically what I've been doing over here. I computed these numbers. This is the probability to the n that n of them are actually sending. This is the probability that n minus n are not sending. And then basically I had to compute these items together. I had to compute the combination, and then from there, the ones that are not computing and the ones that are computing probabilities, and those are the answers. So the probability that, say, 2 are active at a given time is 1.62 times 1 over 10 cubed. Those are the numbers you need to solve the problem, the last problem here. At least I believe that's, yes. It says, suppose there are 120 users. Find the probability at any given time exactly n users are transmitting. Then find the probability that there are 21 or more users transmitting. Now, 21 or more would mean that you have to add the probabilities of if you add the probabilities of 0 up to 20 and subtract it by 1, you get the probability that there are more than 21. So that's the way I would tackle these problems. I'm going to put this out. I'll probably call it something like hints on the homework. I hope that this will mean that you don't have to have the book to solve these particular problems. You might look on the web and look for some of these things. And as I said in my email to you just a short while ago, I will check with the college on Monday to determine if it's not too late for me to get them to pay for the rental of the book I want. If I cannot get that, there is a free textbook on the web that has the material I need, and I would just have to rearrange a few things. So either way, we'll get it taken care of. So work on this for now, and I hope everything is fine. So long now.